Hi guys, in today's lecture we are exploring some of the basic topics of algorithms known as asymptotic notations and recursion. So there are three popular notations in asymptotic notations known as big O, theta and omega, where big O represents the upper bound, omega represents the lower bound and theta represents the uh, both lower and upper bound of a function fn. So that means anytime if we represent the function fn as a big O of gn, then cgn has higher growth than fn after a constant n greater than a constant n naught. So if we like to plot this thing in a graphical fashion, let's see how this upper bound looks like. So we are saying that there is a two-dimensional graph where the size of data is increasing on the x-axis and the time is increasing in the y-axis, and any function fn, okay, usually when you increase the size of data, the time taken should be, usually it increases unless it's not constant time algorithm. So basically when it's working on some data, the fn will have some growth function. So what we are saying is that that there is another function, say gn, where I say with some constant cgn is always above than fn, okay, after a threshold n naught. In other terms, we say cgn is always higher than fn for sufficiently large value of n. Sufficiently large value of n means that n is greater than n naught. So usually whenever we do asymptotic notation or this kind of time complexity analysis, the basic idea of consideration is that n is sufficiently large, because for a small value we can directly compare to functions, but for large value we look for the growth of the function as the n increases to a very high value. So the theta says that fn can be bounded by gn with different constant on upper and lower bound. So c1 gn would be more than fn and c2 gn would be less than fn. Similarly, when we talk about the omega, that provides the lower bound. That means cgn is less than equal to fn. So these all three, omega, theta and big O, represents the bound criteria on fn. Uh, to be precise, it is interesting to see that this bound is having a condition less than equals to. That means the growth of cgn can be equal to fn or more than fn. Now gn can be any higher degree growth function, because the criteria is that gn is more than fn. So if I say fn is some quadratic equation, then gn can include a higher degree polynomial equation. So that means we are precisely saying that gn in case of big O represents tight as well as loose upper bound. Okay, so tight upper bound means that there is no possibility of any upper bound in that criteria, okay, in between. So that is known as the tight upper bound. So let's look this thing with an example here, of fn equals to 3n square plus 5n plus 3000. So there is some algorithm, and based on the calculation, say the time complexity comes as in 3n square plus 5n plus 3000. So one important thing you can note here is that most of the time we are saying that n is sufficiently large. So if I put a very large value of n, say n equals to 10 raised to power 6, that's the size of the data. So whenever an algorithm is created, its complexity is represented in terms of the size of the data. Okay, it can be the number of bits, it can be any other way you are representing your data. So the n is representing the size of the data. Okay, so when I put these values and I say 3 into n square, that is 10 raised to power 6 square plus 5 into 10 raised to power 6 plus 3000, you can see that this is 10 raised to power 12, and in front of 3n square, 5n and 3000 are not of much significance. So even if I see the growth of n square and 5n, you can see that n is something like this. However, the n square would be something like this. So the growth of n square is more than the n, and the value of n is growing here and time is here, or value is here, right? So we can see that these two terms are of not much significance. The only term that is of significance is of 3n square. So that means if I take this term, I can easily identify an upper bound and lower bound, suggesting that say 3n square would be less than equal to 4n square and less than equal to 2n square. Okay, even if I get very small upgraded with 3 plus delta equals to 0.001, this function would be of higher growth than this function. Similarly, a very small decrease in 3 will represent the lower bound. So that means if my fn is equals to this, I can say that my gn would be equals to also equals to n square, or I can represent the complexity as theta of n square. So it is important to see in the case of average case complexity that the function highest or largest function, if it is constant or I say consistent here, and there are no complexity changes based on n or any other constant k, then we can represent the upper and lower bound by the highest growing function of fn. So here that is as coming as theta of n square. Okay, I hope the concept for average case complexity is clear. Now when we talk about two more representation known as little o and little omega, little o represents the loose upper bound. So the only difference here is that now it is not less than equals to, it is strictly less than. That means the growth of function gn is now strictly greater than fn, or similarly in the other case we say the growth of function gn is strictly less than fn. So little o and little omega represents the loose upper bound. So if I have any complexity coming as fn is equals to say n square, and I take any higher degree gn, so that would work in the case of little omega, little o. So we can say fn is equals to little o of n cube, where fn is equals to n square. So these two represents the loose upper and lower bounds. However, the previous one represents the tight and as well as loose lower and upper bound. These three are more popular, and say a user wants to correctly estimate the complexity of their algorithm. So usually these say some algorithm might be tested on a small scale data, and then eventually when user wants to try them on a large scale of data, it is interesting to calculate the correct complexity as close to as possible to the real time consumption, so that correct estimation will provide the correct measures. So means some algorithm taking say 1 hour time or 1 day time or 1 year time is significantly impact your decision making in company. Okay, so let's look at this small practice question, where there is this statement and some three for nested loops. So the basic idea is how many times this statement is executing, or these lines are executing, and without loss of any generality, we can make that every statement consumes some constant time in execution. And as we are not worried about the constant multiplication, as if you have seen that whenever we write gn or fn, those are independent of any multiplication of constant or summation of constant value. So effectively, if we see that this loop executes n by 2 number of times, the idea is always in a nested loop, when you are want to calculate that how many times particular statements are executing, then you always start from the uh, you know the loop which is lowest loop, or I say which is in in last brackets. Okay, so this is the lowermost loop, so I say this runs n by 2 times. Now if we try to calculate that how many times this loop is executing, now this is little interesting, because this loop has a dependency on the upper loop. So when I equals to 1, this loop execute one number of time. When I equals to 2, this runs executes 2 square time, 3 square time, and so on. So based on different I value, it executes different number of times. Now we have already included the impact of this loop when writing the number of times execution of this loop. So that means we don't need to further consider this loop here. So we can say that the complexity is n by 2 multiplied by 1 plus 2 square plus 3 square plus n square. If you know, this is the summation of square of n natural numbers, and can be represented as n into n plus 1 into 2n plus 1 divided by 6. Again, we are not worried about these constant terms or any this type of constant term. Okay, the eventually idea is that whatever be the highest growing function here, that can represents the complexity. So we can directly say that this is n raised to power 4, n into n into n into n. So the highest term we will be getting is theta of n raised to power 4. Okay, so this is it for today's lecture. Thank you so much.